filtration, we were talking about reabsorption. Okay, reabsorption moves stuff from what fluid to what fluid? Filtrate back into the blood, yes. And how about transport mechanisms for reabsorption? Tell me. Cheapest, fastest way is what you do, right? If you could get passive transport, you would do it. If you needed to pay, would you do active or secondary active, primary active or secondary active first? Secondary active first, right? And then primary active when you have to, okay? So we talked first about glucose reabsorption. What was the mechanism, big picture, of how we do glucose reabsorption at the kidney? Secondary active transport, yes? Secondary active transport. And it happens throughout the tube, but it's mostly in the proximal convoluted tubule. Good? Okay. And then we were talking about sodium ion reabsorption, and sodium ion reabsorption is 2 steps, yes? Proximal convoluted tubule reabsorption, how much is reabsorbed and how do you control it? 65%, and you don't control it. Yeah, there is no control. It's obligatory reabsorption or non-regulated reabsorption. Good? Okay. And then the second time you have the opportunity to do reabsorption, if you need to, is in the distal convoluted tubule, yeah? And the distal convoluted tubule does what we call regulated or facultative reabsorption, primarily under the influence of 2 hormones. What are they? Not ADH, we haven't talked about ADH. ADH is not, here's something important. ADH is water reabsorption. This is sodium reabsorption. I agree with you that water generally follows sodium, but not always. We will see that in just a minute. It's aldosterone and ANP. Okay? Renin is one of the triggers for release of aldosterone, but aldosterone is the thing that actually targets the distal convoluted tubule and ANP. Does that make sense? Okay. All right. Got it? Okay. So now what we are going to do is, I think, we did aldosterone and ANP, correct? Okay. So the only other thing that I want to reinforce before we go any further is that when you use aldosterone, and we talked about this last time, and we're talking filtrate. When you use aldosterone, you reabsorb sodium at the expense of either potassium, I cannot write today, or 8+, right? So we will see aldosterone visited one more time when we talk about potassium what? What's the word? Filtration, reabsorption, secretion, excretion. Secretion. Yes. Yeah? Okay. So aldosterone triggers both sodium reabsorption and potassium secretion. Yes, secretion. Good. Okay. So next topic is potassium ion reabsorption. Potassium ion reabsorption happens primarily at the proximal convoluted tubule, almost exclusively at the proximal convoluted tubule. And what happens is we reabsorb about 90% of the potassium that is pushed out via filtration. We reabsorb about 90% of it at the proximal convoluted tubule, and then we can go down from there. We always lose 10%, but we could lose more than 10%. Yes? Okay, so how does this relate to your life? If you are deficient in one of those 2 ions, is it likely to be sodium or potassium? Potassium, and in part because we really like sodium in our food, and in part because we always lose some of the potassium. Does that make sense to you guys? So 90% is reabsorbed in the proximal convoluted tubule. It's active transport, we pay for it. There's no regulated reabsorption of the rest, but there is regulated secretion of the rest. So we lose 10% or more. Yes? If aldosterone was present, how much might we lose? 12%, 15%, something like that. Generally speaking, our reabsorption total mechanism, the total amount that we reabsorb, the amount that's filtered minus the amount that we reabsorb plus the amount that we secrete, we usually end up keeping about 85% of our potassium. We lose about 15% as we go through our kidneys. Okay, so that ends up making a difference, of course, for nutrition and those kinds of things. Okay, how about chloride ion and bicarbonate ion reabsorption? Well, what happens with those is that We don't tend to have to worry about those negative ions reabsorption so much because we actively reabsorb so many positive ions. Does that make sense? Sodium and potassium, that we create an electrical gradient that will allow those to follow if you just give them a channel to move through. Does that make sense? So we work so hard on sodium and potassium reabsorption that we kind of get these for free. Yeah, as long as you provide a channel for them to go through. If, for instance, we move all of these solutes into the bloodstream, we create a massive positive electrical gradient, right? And then the negative ones just follow them in, right? That good? So with the negative ion reabsorptions, we don't usually have to control it directly because we're working on the positive ions directly. Is that okay? Okay, and that's primarily chloride and bicarbonate ions. And then water reabsorption. Okay, put your seatbelts on for water reabsorption. Okay, so water reabsorption happens a couple of ways. The simplest way to say it is that if you create a massive ion movement with sodium, potassium, all of those charged particles, then you are going to create a massive motivation for water to move, right? Because solutes suck and charged solutes suck the most, okay? So as sodium ions are actively transported from the filtrate to the cells, back into the blood plasma, generally speaking, if water can, it will follow it. So let's look at that one more time. Where are we? Okay, so if you're moving all of these solutes, right, they're creating an osmotic gradient for the water, and water will follow when it can. There are situations in which water can't follow, and we'll look at those in just a second. All right, so generally speaking, water is going to try to follow solutes, especially sodium. And so water will follow sodium ions to reestablish the osmotic equilibrium. But there's three different types of water reabsorption. The first one's simple. First one basically says that what sodium does in the proximal convoluted tubule, water will follow. So 65% of, approximately, because there's some that goes on in the tube too, 65% of sodium reabsorption happens at the proximal convoluted tubule, and you have aquaporins in the proximal convoluted tubule, so water will follow at about 65%. And we don't have any control over that either, right? So that's just obligatory or non-regulated reabsorption of water at the proximal convoluted tubule. Push it all out, reabsorb 65% of it. Good? Okay. But then we are going to do the loop of Henle reabsorption, and this is complicated as hell, okay? But I have a video that makes it make quite a bit of sense. Okay, so I'm going to go through it in words, and I'm going to show you the video, okay? All right, so basically what we are going to have as we go through the loop, we are going to have proximal convoluted tubule, stick with me for just a second, then we're going to have the loop. The loop is all about water reabsorption, and it's all osmotically driven. Okay, so we're going to have the descending loop and then the ascending loop, and then it's going to lead to the distal convoluted tubule and the collecting duct, right? Everybody got the anatomy? All right, so what is going to happen is, and this is not going to make a damn bit of sense the first time you hear it, unless if you've heard it before, bravo, you will feel really good today. If you haven't heard it before, you're going to be going, is it too late to drop? Okay, and it is. Okay, so here's the deal. The ascending loop right here is going to actively, stick with me, actively pump ions into the interstitial fluid. Okay? Good. And the ascending loop, notice that it's parallel to the descending loop. Okay? So what is going to happen if you actively pump ions from the tube into the interstitial fluid? What's going to happen to the fluid as it goes through this portion of the loop? If you make the fluid, yeah, so you're going to suck fluid out. And if you run them two opposite directions, you get the counter current culture. The hell, Melanie. Counter current multiplier, because they're running two opposite directions. So we're about to see an animation for it. But if one of the tubes pumps solutes out and then the other tube is porous, then what's going to happen with the other tube is it's going to suck water out via osmosis, right? And the longer they are, the better that is. That is why I think I told you guys at the beginning of the semester that when I took physiology in college, it was comparative animal physiology. And one of the things that we did was compare like desert animals to other animals. Desert animals have super duper long loops of Henle so that they can get all of the benefit of that massive countercurrent multiplier system. Does that make sense? So like a kangaroo rat that lives in the desert, I can't talk today, I should go home, that lives in the desert, they actually reabsorb almost all of their water via this mechanism to the point that their urine is paste. It's like only liquid enough to get it out of the tubes. That's it, right? It's almost like poop because they reabsorb all of the water. Does that make sense? So let's look at one more time in the notes and then we'll watch the animation. Good? Okay, so the ascending loop actively pumps the solutes, primarily sodium but not exclusively, into the extracellular fluid as the solute goes up the loop. The descending loop is only permeable to water and not solutes. Yes? Okay. And which moves from the tubule to the ECF by osmosis as it goes up the loop. I don't know why I said up. As it goes through the loop. Urine is therefore concentrated by the loop of Henle. So let's watch the video. This is the best one I could find because this is one that I'm like, I need somebody to draw pictures for us.
The countercurrent multiplier, also known as the countercurrent exchange system, is the method that the nephron uses to concentrate urine. For a lot of people, just the name of this process is daunting. Countercurrent multiplier sounds like a complicated math formula or something, but it's really much easier than it sounds. To begin with, let's look at the anatomy of the nephron and its place in the kidney. If you recall, the kidney is divided into the outer portion, the cortex, and the inner portion, the medulla. The glomerulus and proximal tubule are located in the outer cortex. The loop of Henle descends down into the medulla of the kidney, loops around, and comes back up. By the time it becomes the distal tubule, it's back in the cortex. The collecting ducts then descend back down into the medulla and eventually empty the filtrate into the calyces and renal pelvis. For starters, I want you to think of the medulla as being very salty. In fact, at the bottom of the loop of Henle, the sodium concentration is about 300 milliequivalents per liter, which is double that of the blood. The loop of Henle has some special characteristics that explain why that is, and it's really all about saving energy. So the descending loop of Henle is extremely permeable to water, but it's impermeable to ions. So water is able to passively diffuse out of the descending limb where it is reabsorbed by the vasa recta, the vessels that surround the loop of Henle. The ascending limb, especially the thick segment, however, is the opposite. It's impermeable to water, but will use energy to actively pump ions like sodium and chloride out of the tubule into the interstitium of the medulla. When it does this, it creates a hypertonic environment around it. Because the descending limb is very permeable to water, water leaves the descending tubule without expending any energy because it is following the concentration gradient. So it is called countercurrent because the filtrate flows in opposite directions, down the descending loop and back up the ascending loop. It is called a multiplier because the active pumping of ions out of the ascending tubule multiplies the amount of water that is reabsorbed from the descending tubule. As more water is pumped out, the filtrate becomes more and more concentrated.
Good? Not do you love it, but is it okay? I think it's actually relatively logical, and you know enough about osmosis.
All right. Remember.
Pushy. So you know enough about osmosis to make that make sense to you guys. The only thing I wish about it is that I just wish that it would have done the ion pumping first and then the water reabsorption, because don't you want to like put away one set of toys before you take out the other, right? I just wish, but it doesn't matter, right? It really doesn't matter because you're looking at it collectively with the amount of water that's reabsorbed. Does it also make sense to you that the longer the loop is, the more water reabsorption you will get, right? So, everybody good? Okay, so That is not controlled by hormones, right? It's just what happens in the distal convoluted tubule is part of the total reabsorption of sodium and chloride. It's just added in to the total reabsorption of sodium and chloride. Everybody okay? And then the water you don't have to pay for because you paid for the sodium and chloride reabsorption. Good? Although, interestingly, the sodium and chloride doesn't go back into the blood quite the same way as it does in other portions of the tubule, but we don't have to worry about that. Everybody good? Okay, so what is the big picture functionality of the loop of Henle? What does it do? Water reabsorption. Yes, water reabsorption primarily by osmosis and not by controlling the water reabsorption so much as controlling the ion reabsorption. Okay, and which portion of the tube does what? Descending is water and ascending is ion. Yeah? Good? Okay. So that's called the countercurrent multiplier. For those of you who are going into pharmacy or planning to go into pre-med or something, that is something that so few people understand, but I think I figured out a way to explain it that actually makes it make sense. Go ahead.
And both are pushing water and sludge into the
Extracellular fluid, and most of it gets picked back up by the vasorecta, capillaries. Yeah? Does that make sense? Everybody good? Okay, you don't seem confused enough. Makes me wonder whether you truly got it or you're just like, what the hell just happened? Go ahead.
So does ion reabsorption also occur in these ascending length? Because we're pumping
Ascending
ion,
limb.
so they pick
Yes,
up
yes. Ion reabsorption. When people are doing that ion reabsorption, they usually just lump it into what happens with the distal convoluted tubule. It's not a large percentage, but because it creates an osmotic gradient, it actually has a large impact on the water. It's not a large percentage of the sodium and the chloride, but it has a pretty dramatic impact on water reabsorption. Good? Go ahead. Rebecca's got a question on her face.
I was just thinking about implications for blood pressure medicine.
Oh, mostly distal convoluted tubule, but there's also, and we're going to talk about blood pressure medication in just a second. Okay, so water reabsorption happened 2 places so far. We got 1 more place to do it. Water reabsorption is important. Yes, we filter out 47 gallons per day. We obviously do a shit ton, that's the physiological term for it, of water reabsorption. Yes. First time is proximal convoluted tubule, no control, right? Second time is loop, right? And that is osmotically controlled, right? But it's not controlled by hormones. And the third time is what we actually get to pick. And the third time is the last possible 35%. By the way, that 65% is kind of added in with the tube. So 65% PCT and tube, because you can't control really either one of those. Yeah? So that's all sort of obligatory reabsorption by 2 different mechanisms. And then the 35% happens primarily at the distal convoluted tubule, and it is potentially hormonally controlled. Okay, so, and you've met the hormones before. I'm not teaching you new hormones at this point because you wouldn't absorb them anyway. So distal convoluted tubule of the remaining 35% can be regulated. The primary hormone that regulates it is ADH, antidiuretic hormone. But it's a weird thing that actually goes on there. So this occurs in the DCT, also a little bit into the collecting duct. If it occurs in the collecting duct, it doesn't go directly into the bloodstream. It just kind of goes into the extracellular fluid, and it might end up in the bloodstream. But it's osmosis, so it's okay, right? So you can move in anywhere that there's an aquaporin. Good? Okay, so what is going to happen in the distal convoluted tubule is the cells of the distal convoluted tubule and or collecting duct must contain ADH. Where's ADH come from? Posterior pituitary for regulated reabsorption. So what ADH does, it's complicated, but I can simplify it. Here's the simple. What ADH does is allows water to follow sodium at the distal convoluted tubule. The mechanism is that ADH actually causes aquaporins to move into the cell membranes of the distal convoluted tubule cells. Yeah, I know, right? And I think your textbook had a picture of that. I wonder if, yeah, I didn't put it up there because it looked like it would make people cry. So you don't have to know very much about it, but FYI, when ADH is present, aquaporins were already made, but they were not loaded into the cell membrane. As soon as ADH is present, those pre-made aquaporin proteins get moved into the cell membrane, and then they cause it to be permeable, which is kind of freaking cool. Yes, it is. It's by a cyclic AMP messenger system. It's complicated, but it's cool. So basically, what happens is in the absence of ADH, water cannot follow sodium even if it wants to. In the presence of ADH, water can and does follow sodium because there are aquaporins present. That's part of how we discovered that aquaporins were a thing. We're like, what the hell is going on there? I thought that water followed sodium. And they're like, it needs permission. Permission is ADH. Go ahead.
So aquaporins are respiratory.
Well,
Kind of.
there, every protein is made on the ribosomes of the cell, ultimately, right? But they just didn't finish putting it in position until the presence of ADH, which initiates the last portion in which you load it into the cell membrane.
But other cells in the body we talked about have them.
Have what?
Have aquaporins.
They
We
do.
talked about other.
Do you want to see it? I'll show you. Wait. I won't test you over this because it's too late to drop. Where the hell are you, aquaporins? Oh, there it is. Look at these little bastards. ADH. Magic! Aquaporins. No, it's a G protein cyclic AMP system. It's science. It looks like magic until you look really close. Yeah? That's like all magic. Yeah? It's cool, right? I mean, I'm not going to test you over this portion, but I am going to say that in the absence of ADH, water will not follow sodium at the distal convoluted tubule because aquaporins are not present. Yeah? Go ahead.
I'm sorry, I know you said you're not testing this, but does it also do the aquaporin 3 or is it just aquaporin?
I think it's the aquaporin 2s, but I actually haven't read this research in a while, and I don't usually teach it in this detail in this class, so I'll look it up. But I think it's aquaporin 3s, but I'm not sure. Okay, so if ADH secretion is low, yeah? Okay, so for instance, if some of the 2 days this month that I drank enough water, right? Then I felt really good about myself those 2 days. Then water can't pass through the distal convoluted tubule even if you reabsorb sodium. And by the way, that does happen when you drink tons of water, is that you flush sodium out of your system, but you don't need any more water reabsorption, right? So you need sodium reabsorption in the absence of water reabsorption, yes? Okay, so water cannot pass through the distal convoluted tubule cell membranes even if sodium ion reabsorption. So ADH has the capacity to couple or uncouple sodium and water reabsorption. That's why every single time you guys tried to tell me that ADH was for, or aldosterone was for water reabsorption, I kept correcting you because aldosterone is for sodium reabsorption. Yes? Water follows sodium everywhere that aquaporins exist, but they don't exist in the distal convoluted tubule in the absence of ADH. Yes? So you have to sort of be able to separate them and also put them back together conceptually. So if ADH secretion of water is low, then you pee a lot, yes? Large quantities of dilute urine in which it's like just totally toilet colored. That's a good day, man. I had 2 of those. That's called polyuria, yeah? And she has them every day. Every damn day. She's like hits her urine goal. Right? I mean, that's the least that I could expect of myself as a grown-ass person. 5 of those? 5 of those? Oh my God, that makes me want to yak just thinking about it. So what about diabetes insipidus? Circling back to diabetes insipidus. So with a person who genetically, autoimmunically, cannot secrete adequate amounts of ADH, then they will have chronic polyuria, yeah? Because they can't absorb that last 35%. Yes? Does that make sense? So they are going to be constantly peeing really, really low concentration urine, right? They're going to be constantly peeing it out. So that's called diabetes insipidus. There's a text box about it in your textbook. But if I am like me the other 28 days of the month, what happens is ADH secretion would be high because I was chronically a little bit dehydrated. Then what happens, ADH targets the distal convoluted tubule, allows most to all of that 35% to be reabsorbed by making sure that the aquaporins are there, yeah? And then the final urine volume is small and concentrated, yeah? And ADH also triggers the thirst response. It doesn't really help if you drink more coffee, though, I've figured out. That doesn't help. But it's tastier. Let's just acknowledge that. Okay, so we know this. ADH release is controlled mainly by the water concentration or the osmolarity of the blood that's detected in the hypothalamus. So just to remind you of stuff that you already knew, if water concentration is low, like your blood plasma was hypertonic, then the posterior pituitary would release ADH and water would get reabsorbed, or vice versa would also be true, right? ADH, by the way, is also released if the blood volume, irrespective of the tonicity of the blood, is low, or the blood pressure is low. So there's like 3 triggers that could trigger ADH release. Everybody okay? Okay. All right, go ahead.
That would be part of those reflexes, like the blood reflexes in the vessels.
No, because it's hormonal. Blood reflexes are primarily either paracrine or nervous, I think. Okay, what about reabsorption of other stuff? Yeah, reabsorption of other stuff is kind of based on concentration of the stuff, solubility of the stuff, and the presence or absence of a transport protein for the stuff. So, lipid-soluble substances. Are your kidneys good at clearing lipid-soluble substances? They are absolutely not, because lipid-soluble substances do whatever the hell they want everywhere they are. So, fatty acids, lipid-soluble drugs, lipid-soluble toxins, lipid-soluble poisons, those are really difficult to clear out of the body, and your kidneys are very little help at doing that. Your liver is way more help at doing that than your kidneys are. The liver can help by temporarily changing the structure so it's less lipid-soluble, so it's easier to clear at the kidneys. And then substances that are not lipid-soluble or have no carrier molecule or are too big to be reabsorbed are not reabsorbed or reabsorbed incompletely. For example, urea and uric acid, those are waste products from primarily protein metabolism, are reabsorbed incompletely because of the amount of carrier proteins that we have for those. But it's okay because they actually have another function in the body. And then creatinine from creatine phosphate is not reabsorbed at all. So if you push it out, there's no mechanism for reabsorption, so it just stays out there. Does that make sense? Okay, so everybody okay? Okay, so let's go back one more time and talk about water reabsorption. 3-step water reabsorption. Proximal convoluted tubule water reabsorption, how much and what mechanism? 65%, primarily just following sodium, right? It's just osmosis, following sodium, right? Sodium moves at 65%, aquaporins are present, it moves at 65% as well. Loop, what happens there? Magic? Countercurrent multiplier, right? In which in one limb you're actually pumping solutes and the other ones they're sucking water. And then distal convoluted tubule and duct reabsorption happens by what mechanism? It's still osmosis, and it's following solutes, right? But you actually are going to need what hormone? ADH, in order for the aquaporins to be present. Does that make sense? Okay, so 3-step water reabsorption. That's probably the most complicated reabsorption mechanism. Okay, all right, everybody good? Okay, now we're finished with most of the complicated stuff. All we have to do now is talk about secretion. And secretion is far less of a complicated story, at least as you learn it in this class. So when you are talking about secretion, we're going to call it tubular secretion because it happens at the tube. And secretion can occur anywhere in the tube, but a disproportionate amount of secretion occurs at the last portion of the tube. And it kind of makes sense because then you kind of know what you're dealing with by the time you're almost done, and then you can decide what needs to go at that point. But there are some things that are secreted at different points in the tube. It is going to move stuff from what fluid to what fluid? Blood back into the filtrate. It's going to be selective. Remember our metaphor? This time we're going through all the cabinets in the house, looking under the beds, seeing if anything else needs to go, and we are going to select it. So it's moving things the same direction as filtration, but by totally different mechanisms, not pressure driven, yeah? Okay, so the 2 major effects are controlling blood pH and getting rid of certain materials that you don't filter completely, right? So if I still had any ammonium ion, I could get rid of it by secretion. Some breakdown products, some drugs, actually you get rid of by secretion because they don't get rid of them completely by filtration. Penicillin, phenobarbital. urea and uric acid that was resorbed into the tubule but not needed for pH control, you get rid of. And then excess potassium, you'll get rid of that if you have aldosterone present. Because, again, aldosterone causes sodium blank and potassium blank. Sodium reabsorption and potassium secretion. Good. Okay, aldosterone's from where? Adrenal cortex. And it's, of course, exchanged for sodium. Good. And then last but not least, you are going to control blood pH primarily by deciding how much H plus to hold on to versus secrete. Okay, you ready? And you've done this whole equation before, but now we're just going to stick it into the kidney tubules. Okay, so here's what's going to happen. Inside the epithelial cells of the kidney tubules, primarily but not exclusively the distal convoluted tubule, what I'm going to do is, watch, force this reaction this way and then decide what to do with those two. Does that make sense? Okay. Pretty simple, right? So what I can do is, even if the H plus did not come from carbon dioxide, I've got a tremendous amount of control over pH at the kidneys by forcing this equation and then deciding either to reabsorb buffers or to reabsorb H plus. Buffers, H plus. Does that make sense? Okay. Do you see how much control you could have over pH? Right? Okay, so inside the epithelial cells of the tubule, you are going to do this. And let's say that your blood was too acidic. Then I would actively secrete the H plus via active transport. I would actively reabsorb the bicarbonate ion. And it can buffer H pluses from other things, right? Right? That low blood pH could be due to too many H pluses from whatever source. It could be due to too much carbon dioxide. It could be due to lactic acid from breakdown after skeletal muscle contraction. It could be due to any number of things. But since the kidney can force this reaction and then decide what to do with those two, it has tremendous control over the pH of the body. The only other thing that has anywhere near that control is your lungs. And we'll get to that in just a minute. Everybody good? Okay, so here's a summary, and then there's going to be a summary of a summary. Okay, so what happens in the proximal convoluted tubule is whatever happens in the proximal convoluted tubule, right? And you can't manipulate it. You with me? What happens in the distal convoluted tubule, let's summarize it. What happens in the distal convoluted tubule? In the distal convoluted tubule, when aldosterone and ADH are present, this is what occurs. Sodium is reabsorbed from the filtrate tubular cells back into the bloodstream, but the movement of the positively charged ions must be canceled out by one mechanism or another. Either you can move positives in and move negatives in with them, or you can swap positives for positives. Okay? So water will follow sodium as long as ADH is present. So in the distal convoluted tubule, sodium is reabsorbed, chloride and bicarbonate are reabsorbed. They follow the sodium in. The rest of the sodium moving in has to be balanced by swapping it for another positive, like that situation. Yeah? Okay? So I'm going to move sodium in. I'm going to follow it with negatives, or I'm going to swap it for another positive. And then I end up keeping the electrochemical gradient, right, that I wanted. So the summary of the summary is, at the distal convoluted tubule, when ADH and aldosterone are present, sodium, chloride, bicarbonate, and water are reabsorbed, and potassium and H plus are secreted. Does that make sense? Okay? No? Yes? Yes? At the distal convoluted tubule, when ADH and aldosterone are present, sodium, okay, chloride, bicarbonate, those are just following the positives in, and water, because of ADH, are reabsorbed. So this one is because of aldosterone, this one is because of ADH, okay? And whatever you don't balance out by following the positive with the negative, you'll follow by swapping positives. So potassium and H plus are secreted. Good? Okay. Okay, I don't believe you. Okay. Moving on. Okay, this part's not bad. So we're finished with all the hard parts. The hard parts, FYI, for when you're studying, are absorption and a little bit of secretion. But secretion really depends on you already understanding absorption. So make sure you got filtration, then do absorption, really detailed, And then secretion actually makes a lot of sense after you do absorption. Okay? All right, so how much do you pee per day? On average, about 1,000 mils to 1,800 mils, okay, per day. So about 1 liter to 2 liters per day. But it is impacted by multiple things. It is impacted by blood pressure, by blood concentration, and by some other things. So this is not going to be hard for you. This is going to make sense to you. Okay, so your blood pressure will be directly correlated to how much pee you make because it impacts choose filtration, reabsorption, or secretion. Filtration, yeah? So GFR varies with blood pressure. Increase the blood pressure, you increase the filtration. Increase the filtration, you generally increase the urine volume. Yes? This is one of the reasons why chronic hypertension is very, very hard on your kidneys if left untreated. Okay? It really, really makes your kidneys do tons of filtration, and then they try super hard to do reabsorption to counteract that. In addition, you can actually bust open your glomeruli with chronic hypertension as well. So chronic hypertension untreated can and does often lead to kidney failure. So it's something that's a bigger deal than people imagine it to be. And then, of course, blood pressure is regulated by the renin-angiotensin-aldosterone system, yeah, which is triggered by low blood pressure, right? And if you trigger it by low blood pressure, that's a negative feedback mechanism. And it's going to decrease your urine volume and increase your blood volume. Okay, and then the blood concentration. So what happens, you already know if you drink a lot, you pee a lot. All I'm asking you to do right here is to put together the mechanism by which if you drink a lot, you pee a lot, right? And if you don't drink very much, you don't pee very much. Because what doesn't happen is I drink it, it goes straight out my kidneys. No, that's not what happens, right? You drink it, it gets absorbed, circulates through your bloodstream, then it goes to your kidneys, and certain things happen or don't happen at your kidneys. So let's just look at it. What's happening in Jen every damn day is that she drinks boatloads of water, and then the water concentration of her blood increases, right? It becomes hypotonic, for instance. And then ADH secretion is inhibited, yes? And then water reabsorption in the distal convoluted tubule and the collecting duct can't follow sodium reabsorption because of the lack of what hormone? ADH, exactly. Sodium ion reabsorption can be normal because that's controlled by aldosterone. Water reabsorption of the distal convoluted tubule, not. Okay, so large amounts of dilute urine is excreted. So yes, you were right. If you drink a lot, you pee a lot, but it's because of this hormone right here. Yeah, the lack of that hormone being secreted. If you are dehydrated, the water concentration of your blood decreases, hypertonic, yes, and then ADH is secreted. It targets the distal convoluted tubule and the collecting duct, loads up those aquaporins, right? And then you get water reabsorption of the distal convoluted tubule and you don't pee as much. So if you don't drink a lot, you don't pee a lot because of ADH. Yes? Okay. And then temperature. So anybody who camps has experienced this. What is going to happen when it's negative 22 degrees and you're camping in a damn tent in the middle of the night? What's going to happen? You have to pee. You always have to pee in the middle of the night and you can't find your damn shoes. Right? And then if you're a woman, you pee on your shoes. You know you do. You have pee shoes. They're camping shoes. That's what they are. They're splashing going everywhere. I grab my husband's shoes, but don't tell him. They're really big. They're easy to find, you know. Okay, I don't. He would murder me. So when exposed to high temperatures, what occurs? So when exposed to high temperatures, what occurs is your cutaneous vessels will dilate to cool you down. You're going to sweat and lose fluid and ions that way. Since you're sweating and losing fluid and ions that way, you don't need to lose fluid and ions at your kidneys. So as the fluid in the body decreases, ADH and potentially aldosterone is going to be secreted because you lost salt as well. So you need to hold on to salt at your kidneys. And so the regulated reabsorption of sodium and water is going to increase. So when you're hot, you sweat a lot and you don't pee a lot. Yes? Does that make sense? Okay. What about when you're cold? When you're cold, you do peripheral vasoconstriction, which increases the pressure in this body cavity. And as you increase the pressure in this body cavity, which thing is impacted? Filtration, reabsorption, secretion. Filtration, yes. You increase the GFR. So your cutaneous vessels will constrict and blood is shunted to your abdominal vessels. More blood goes to the glomeruli, increased GFR, increased urine volume. It's irritating, isn't it? Yes? Okay, now let's talk about diuretics. And then we'll talk about renal calculi and we'll be done. Okay, how do diuretics work? So this is kind of interesting. And of course you guys are going to deal with diuretics if you're going into human health, right? You definitely are going to be. You're in the United States and half of everybody has a hypertension problem here. So what is going to occur is you can control, let's just think about it before we get into it. You can try, at least theoretically, to control sodium reabsorption and or water reabsorption. You can try to control it here, here, or here. Yeah? So let's figure out how the diuretics actually do it. So there's different kinds of diuretics. Some diuretics inhibit PCT reabsorption of sodium. Now, I told you it was non-regulated. It's non-regulated by any mechanism that you make, but we actually did figure out some drugs that can impact non-regulated reabsorption. That's 65%. They're going to be super duper good diuretics, right? Because they can inhibit 65% of sodium and therefore water reabsorption at the distal convoluted tubule. So that's going to be massively effective. But it has this sort of perhaps originally unpredicted consequence in that what happens is if you don't reabsorb it here, you're going to deliver it here and then deliver it here, and then your body's going to go, WTF, we need to do some sodium reabsorption. So what it's going to do is try to do all of the possible sodium reabsorption at the distal convoluted tubule, but every time you do, it's going to cost you one of these. So the problem is that these are super duper effective at inhibiting proximal convoluted tubule sodium and water reabsorption, but your body tries to compensate by doing massive distal convoluted tubule sodium and water reabsorption, and it causes potassium and pH disturbances. So do you know those diuretics that you can be on in the hospital like Lasix, that they also give you a potassium drip with? Yes? Because they are super duper effective, but they cost you potassium. Does that make sense? Yeah? You also have to monitor your blood pH when you're dealing with those as well. Does that make sense to you guys? No? Yes? You are not giving me any feedback today. You haven't even had any mashed potatoes yet. Your brain should totally work still. Okay? No? Yes? Somebody ask a question. I want a clarifying question. Or at least a restatement of what I just said. Okay? No? Okay. Somebody try. Where do these, like Lasix, which is spironolactone, I think?
So what situation?
No, hydrochlorothiazide.
What
Hydrochlorothiazide.
situation would you use this application in? Of where
Oh,
you need to
really commonly in the hospital, right? Generally speaking, when people are using something that's this massively effective, either they're really regularly being cared for or they're actually admitted into the hospital, in part because it can cause massive potassium disturbances. So if you have somebody who goes into the hospital and they have a lot of fluid retention and you really, really need to get rid of that fluid really quickly, you're going to give them a really, really effective diuretic, but you have to watch their potassium concentration. Otherwise, they'll get hypokalemia.
So would that be someone with really bad edema? Or
Oh, yeah. Mm-hmm. Yeah.
edema who had circulatory problems and they just were puffing up?
Yes, exactly. But there's also all kinds of cardiovascular disorders that are complicated by other treatments that you can use this simultaneously. But you're going to be watching your potassium concentration. What were you going to say, Rebecca?
Lasix is furosemide.
Okay, so this one's similar to Lasix. So hydrochlorothiazide. Okay, so these are your diuretics that have the risk of a dangerous loss of potassium associated with them. Now, the other diuretics are not as effective, but also not as risky. Think about this. See, maybe it'll reinforce the other one. These diuretics are going to lead to proximal convoluted tubule reabsorption of sodium and water alone. Yeah? So you don't have control of that 65% with these drugs, but you do have the ability to inhibit the 35% reabsorption. So before we go any further, can you see that these are not going to have as massive and quick an impact as the other ones? Yes? So all they can do is this 35%. But they are also not going to force you to lose potassium because they are going to inhibit this, not encourage that. Yes? Okay? So these drugs right here, you can use as maintenance medications without being as risky, yes? And so you can have a prescription pill that is this kind of a diuretic, yeah? So those interfere with aldosterone. Some extra sodium and water are lost from the body, but potassium ions are not impacted. These are not as effective as these, but they are safer. These are called potassium-sparing diuretics. Go ahead.
I think hydrochlorothiazide is potassium sparing diuretic.
Oh, I'll look it up. Okay, I'll figure it out. If that's wrong, don't worry about it. So the mechanism is fine. The mechanism still works. Okay, so how about other diuretics that you don't necessarily take to be a diuretic? Why is alcohol a diuretic? Alcohol is the diuretic for a couple of different reasons. It actually impacts your blood pressure in some places, but it also inhibits ADH secretion. So it's actually an anti-diuretic is what it is. Yeah? Inhibits ADH secretion, and since it inhibits ADH secretion, it inhibits water following sodium at the distal convoluted tubule. Does that make sense? So how about caffeine? We know that caffeine is a diuretic, right? Caffeine is a diuretic because it increases blood flow to the kidneys. So what does it do? Increase filtration, reabsorption, secretion. Filtration. Increases filtration. Yep. Okay, that's how that one works. And then we have the osmotic diuretics. And the osmotic diuretics are usually, the ones that I know of are sold over the counter. And women may have been more likely to take these, like water pills for when you're really, really retaining a lot of water during your menstrual cycle, right? And you can take them, and sometimes they're associated with PMS pills like Premarin or something. They have a little bit of a diuretic in them. But here's how they work. They are an osmotic diuretic in that you take them, and they are a molecule that gets filtered out and has no reabsorption mechanism. So as it goes through the tube, it exerts an osmotic effect as it goes through the tube, and it just sucks fluid into the tube, kind of like glucose in an untreated diabetic. Does that make sense? So these are called osmotic diuretics, and unless I got this one wrong too, mannitol is one of them. They are less risky than these two because they're not as massively effective. But do not think that you can't kill yourself with one of these. You totally can kill yourself with one of these. If you are taking them as directed, you're not supposed to take them for long periods of time. Sometimes when people are bulimic and or anorexic, they will use these to the point that they really, really impact their water concentration in the bloodstream, which can cause nervous system disturbances. They can also cause ion composition disturbances, and you can kill yourself with enough of these. So you can actually go into circulatory system shock because of the loss of fluid, and you can have hyponatremia, impact the brain. So I'm not saying they're not dangerous. They are not generally dangerous when used as indicated, okay, as you're supposed to indicate those. So that's an osmotic diuretic. Everybody good? Okay, last little tidbit before we leave the urinary system is just to talk about kidney stones. Ooh, kidney stones. Those little bastards. How many of you guys have had them? Anybody had kidney stones? Oh, damn it. There's a genetic predisposition to kidney stones. It's also hormonally impacted. What? Oh, your grandma has them. Thanks, Grandma. Could have given me a freaking car. Gave me some kidney stones. Okay. Oh, where the hell are they? Did I lose my kidney stones?
How are they hormonally impacted, the kidney stones, hormones?
Because your hormones impact your ion compositions, yeah, and your ion composition impacts how many ions are in your urine. So hold on to that question for just a second. Okay, so renal calculi. Here's what happens with renal calculi. Generally speaking, renal calculi are going to form as you get crystalline formations, ions, yes, that form in your minor or major calyces or in your renal pelvis. But then those little bastards have to go all the way through the tube and on the way out. And in this situation, we are so happy not to have penises, gentlemen, because we have a 4-centimeter urethra, right? Right? And it's got to get out through the whole damn thing. So it has to go all the way through the ureters, and then it doesn't usually cause problems most of the time when it's in your urinary bladder, unless it's one of these little bastards. Look at that. Damn. I don't know what you did in your past life, but you need to clean that up. But then as it goes through their urethra, it can be super duper painful. Now they can break it up, right? They can shoot some sonar waves at it, but that means you have to pass more smaller ones instead of one big one. So what happens, the conditions that are leading to formation of kidney stones are, like me, if you don't drink enough water, then you're more likely to have concentrated ions forming crystals, in your kidneys. But also, if you impact the acidity of your urine, crystals form in different pHs, predisposition. So abnormally alkaline urine, abnormally acidic urine, primarily based on your diet. Ingestion of excessive mineral salts, if you're taking in tons and tons of certain kinds of ions. Overactivity of parathyroid glands. Parathyroid hormone will mobilize calcium ions and phosphorus ions from your bones. And this one I put a question mark for, not because we don't know there's a correlation, it's because we don't completely understand the causative mechanism. We do know that sodas, especially diet sodas, are very, very salty, and they also impact the pH of your bloodstream, and they increase your likelihood of forming kidney stones. Sugar sodas, yes, and diet sodas even more because they're even saltier, right? And then what's the prevention for kidney stones? Drink lots of fluid, Melanie, especially before bedtime because it just sits there in your renal pelvis. I know, right? Annoying. Do not limit intake of anions such as oxalate or urate. Limit intake of anions, but don't limit intake of like calcium and potassium. Sodium, most of us can use limiting intake, but the other ones not so much. And then we already talked about dialysis. Dialysis is what you do when your kidneys are not actually doing their function, but it's based on diffusion, not filtration. Everybody good? Okay. I will look up what Rebecca said and fix that. I'll just figure out which one works by which mechanism. I literally looked it up over the summer, though. I don't know how I got it wrong.
Well, the only reason I know that one for sure is because when I was talking to my pharmacist about it the other day, and when we were talking about potassium and the sodium potassium pump, he was like, "No, that one's potassium sparing." Oh,
okay. I'll go look it up. First time I've ever been wrong about anything. Just today, right? Okay. All right. So respiratory system. Respiratory system is next. Last set of notes. It's not even that complicated. It's not horrible, okay? Most of it, respiratory system understanding primarily depends on you understanding cardiovascular physiology and a little bit of urinary physiology, and if you've got those, you're okay. And, okay, so let us start with Roman numeral 2 with just some terminology with the concept of respiration and the terminology associated with respiration. And hopefully you guys got this in lab as well. I don't know how much of the terminology you actually grasped in lab. I never know how much you guys grasp in lab. So we'll see. I'll ask you some specific questions on the summary thing. Okay, so we're talking about the respiratory system, but let's define respiration. And also the sub-definitions include ventilation. So here's the deal. External respiration and internal respiration. So the entire semester, we have really been talking about serving internal respiration, because what internal respiration is cellular respiration. It is at the cellular level taking in oxygen and delivering carbon dioxide out, yes? But what we are going to do with external respiration is we are going to serve cellular respiration, right? But external respiration starts with breathing, and breathing is ventilation. Yes, ventilation. And breathing is like interesting physics to me. I don't know why the hell I like it. Probably because I love space so much. And I like to think about how you would be able to breathe or not breathe on other planets. Because it's all pressure driven, right? So with ventilation, we're about to get into ventilation. All you really do is change the pressure in this cavity right here relative to a relatively constant pressure out here, right? And air moves like fluids move from high pressure to low pressure. So if the pressure is lower in here, then air passively moves in. Yes? If the pressure is higher in here, then air passively moves out. Yes? Good? Okay. But that, of course, depends on this sort of relatively dependable atmospheric pressure based on this planet that we're on. Okay. So that is ventilation. We're going to get into that first. And then after you've done ventilation, once you get the air in, Then you need to do the gas exchange, yeah? And that is involved with 2 different gas exchanges, primarily just diffusion from the alveoli into the capillary bed, down what you think of as concentration gradients. Physiologists call them partial pressure gradients. And so we're going to do that at the lungs. Then we're going to do circulation. Then we're going to do the gas exchange again at your systemic capillaries, okay? And all of that is involved in the process that we call external respiration. And then internal respiration is cellular respiration. So let's do the physics part first that I find really interesting. So ventilation and the concept of lung mechanics. And a lot of this you already understand, but I just want to make sure that you can feel it and put it together with your own body today. Okay, so the process of inspiration, the lung mechanics associated with inspiration have to do with some skeletal muscles, primarily, right? And so what we are going to have with skeletal muscles is the muscles of ventilation are going to be the intercostal muscles and then the diaphragm. So what you are going to do is you are going to just use a little physics to change the size and pressure of this container relative to the pressure out here. So what we are going to do is change the size of the thoracic cavity in response to contracting the diaphragm and the external intercostal muscles. So you guys probably already know this, but when you breathe in, what you're going to do is you're going to take your diaphragm from being bell-shaped, yeah, to being flat. As you do that, what you are going to do is change the size of a container that contains gases, yes? And volume and size, right? And pressure. Volume and pressure are inversely correlated. So as I increase the volume of the container, I decrease the pressure in the container. So what I'm going to do is I'm going to move the diaphragm down, and then the external intercostals are out here, right? They're external in 2 ways. They're both more superficial and more lateral. What they are going to do is pull up and out the thoracic cavity, again, increasing the size of the container. So I took a container that had gas in it, and I made the volume of the container bigger, which means I made the pressure lower, right? And all I need to do is drop the pressure slightly below atmospheric pressure, and then air will passively move in. And that's the process of inspiration. Good? So the increase in the size of the thorax causes a decrease in air pressure in this in the thoracic cavity, but we also have to get to another concept. And so let's get to this other concept, and we're going to talk about it in more detail later. This works really well for increasing the size of the thoracic cavity, but in order to make air move into the lungs, what you have to do is make the lungs follow what the thoracic cavity is doing. So, and this is not the last time you're going to hear it, I have between the visceral and the parietal pleura, I have fluid, yes? Okay, and I've got serous fluid in there. In a healthy person, during the development of your respiratory system, this pressure should be low enough that they stay adhered to one another like 2 glass slides, right? You've tried to pull glass slides apart. So what should happen is the fluid in here and the negative, what we call intrapleural pressure, should make it so that when I suck out the walls of my thoracic cavities, my lungs get sucked out with it. Does that make sense to you? Okay. That only happens if the pressure in the intrapleural space is negative, meaning it has to be lower than atmospheric pressure. That is all well and good because it develops naturally with you guys, and it only causes problems if something equalizes the pressure by, for instance, a pneumothorax. Then what is going to happen is these elastic structures are going to collapse onto themselves because this pressure equaled atmospheric pressure instead of being a vacuum. Okay, so in order to collapse a lung, we will see that you don't even have to touch the damn thing. All you have to do is allow atmospheric pressure into the pleural cavity, and then the elasticity of the lung will collapse down on itself. What's your question face going on?
Nope, that's my damn face.
Oh, yeah. Okay, so.
Always has to stay at a negative pressure.
Yes, it does. Yeah, I'll talk about that in just a second. So hold on to that question. Okay, so this also brings us to the concept of lung compliance. And the term compliance basically means how stretchy are you. It's both with vessels and with lungs. So what the lungs should do in a healthy person, we'll come back to the person who had a pneumothorax, is that when you pull out, they should be stretchy enough to sort of follow what your thoracic cavity is doing. But then when you relax your diaphragm and your intercostal muscles, they should also have some snapback, yeah, that helps to push air back out. Healthy lungs are really compliant. Cancerous lungs, for instance, or lungs with tuberculosis or lungs with emphysema get scar tissue in their wall and they lose compliance, among other things. Good? So that's the concept of lung compliance. So the walls of the lungs are sucked out by decreased air pressure, the airspace volume in the lungs increases, the increased volume inside the lungs causes decreased air pressure, and the air moves in as it goes below atmospheric pressure, so air rushes in. Then how does expiration or exhalation work? Most of the time, it's just a passive process, okay? Meaning that all I have to do to increase the pressure in here above the pressure out here is relax the diaphragm and relax the external intercostal muscles. The volume decreases, the pressure increases. That's generally enough to move air out, right? Because it moves from high pressure to low pressure. Now, normally expiration is a passive process, but when you're talking, when you're blowing out a birthday candle, when you're exercising, then what you are going to need is more exhalation than you provide than just a passive process. And then you'll do forced expiration, and forced expiration is primarily squishing together your internal intercostal muscles to, again, make the volume of the container slightly smaller and therefore the pressure slightly higher, yeah? So you can force air out because there's a bigger pressure gradient. You also can help it if you push on your abdominal muscles, right? And you can pull these closer together and push on the diaphragm from the bottom, right? And then you can force air out. But forced exhalation does not happen with normal tidal breathing, right? Normal tidal breathing is just active inspiration, passive expiration. Does that make sense? Yeah, got it? Okay, so let's look at the mechanics of pulmonary ventilation. It looks like math, but it's not. Okay, so with the mechanics of pulmonary ventilation, ventilation is the exchange of air, not the exchange of oxygen and carbon dioxide, right? So I'm moving air, atmospheric air, all of them, carbon, oxygen, nitrogen, water gas, all of those are moving in, yes? I have to get the air into the lungs before I can have the concentration gradient that might make it move into the bloodstream. So I'm moving air when I'm talking about ventilation. So the flow of air into and out of the lungs is governed by three principles. The first one is that air flows from high pressure to low pressure. So this should look like a very, very similar equation to you. So this is airflow. It's F equals delta P, only we'll be more specific about it because the delta P is always the difference between two specific pressures. It's atmospheric pressure minus alveolar pressure. Okay, so let's just think about this. I mean, it's going to make sense anyway. If atmospheric pressure is greater than alveolar pressure, then air is going to move in, yeah? If alveolar pressure is greater than atmospheric pressure, then air is going to move out. This can be impacted, of course, by resistance. And resistance is the opposition to flow that primarily occurs in the tube. And it'll have things to do with like asthma and bronchitis, yeah? All those kinds of things, anything that can gunk up the tube or narrow the tube, right? So F equals delta P over R. Atmospheric pressure is generally a constant 760 millimeters of mercury. Now, it does differ at different elevations, right? But it's not going to differ dramatically over the course of a few minutes, right? Once you standardize to whatever elevation you're at, it's relatively constant over short periods of time. And then alveolar pressure is the intra-alveolar pressure, the pressure inside an alveolus. At rest, meaning between breaths, by definition, alveolar pressure is equal to atmospheric pressure. Does that make sense to you? So look here. Where's that picture? Okay, so just conceptually, here is what is going to happen. So as alveolar pressure drops below atmospheric pressure, which is the zero because that's the constant, right? Then air is going to move in. That's inspiration. Here's between breaths. It's the same, so no air is moving, right? As alveolar pressure goes above atmospheric pressure, then air moves out. Does that make sense to you? So all you are doing is changing the pressure in here just slightly above and just slightly below atmospheric pressure so that air moves in and air moves out, right? So between breaths, alveolar pressure by definition is equal to atmospheric pressure because it's not moving anywhere, right? If there was a pressure gradient, it would be moving. Go ahead.
The atmospheric pressure is 760,
Uh-huh.
so 0 is just a simple
Yeah, so by the way, I'm actually kind of glad that they do this. When they look at pressures, when they're talking about ventilation, they just set atmospheric pressure as 0, so you don't have to keep track of 761 versus 759, because really all you have to do is pop 1 millimeter of mercury above and air will move out, 1 millimeter of mercury below and air will move in. So they just set it at 0 to keep things simple. But it's 760 millimeters of mercury, generally speaking. So we'll come back to that in just a second. So the thing that you already know is that changes in volume will cause changes in pressure, and changes in pressure will cause flow. Yeah? Good? Okay, so this is Boyle's gas law. Did you guys learn this in physics? Yeah? Boyle's gas law basically says that if you have a container and you squish it, the pressure increases as the volume decreases. And if you have a container and you stretch it, the pressure decreases as the volume increases. So it's a inverse relationship between pressure and volume. So the movement of air into the lungs is, of course, opposed by resistance. And we'll come back to resistance in just a second. So last little tidbit is just to put some definitions to the stuff that we've already talked about. So the muscles of ventilation are primarily the diaphragm and the intercostal muscles. Contraction of those muscles causes changes in volume, which causes changes in pressure, which causes ventilation, causes air to move. And so basically, if you just looked at it here, and if you said, like we said before, if alveolar pressure is less than atmospheric pressure, then air will move in. That's inspiration. If alveolar pressure is greater than atmospheric pressure, then air will move out, and that's expiration. And the last thing to cover today is just to make sure that we can talk about this one last time. Okay, so one last time. What we have been talking about this whole time is changing the size of the thoracic cavity, But in order to make this actually impact the alveoli, we have to make the lungs stay stuck to the wall of the thoracic cavity, which brings us back one more time to the concept of what about this pressure right here in the intrapleural space? So the pressure in the intrapleural space is called intrapleural pressure, okay? It's the pressure in the fluid. This creates surface tension, and negative pressure in that area from the serous fluid keeps the lungs from separating from the thoracic cavity as you increase the size of the thoracic cavity, right? But in order to make that occur, this pressure needs to be negative. So let's go back to this picture one more time and say, okay, healthy person right here, the pressure, the intrapleural pressure is a vacuum, -4, right, compared to atmospheric pressure, okay? As long as it stays that way, then you can depend on that negative pressure and hydrogen bonding to keep the lungs stuck to the thoracic cavity, right? If, however, you equal that, the compliance of the lungs will work against you. You will lose that adherence to the wall and the lung will collapse on itself without even touching the lung itself because of the compliance of the lungs. Does that make sense? Okay, good? All right, so I will see you guys on Tuesday. Yeah, and Tuesday's our last lecture. I'm gonna, for those of you who feel a little overwhelmed, I would watch videos from last semester before you get here on Tuesday. So it won't be the first time you hear it, because is there any possibility of us moving that test? Zero possibility. And am I going to take off any of this material? No, I'm not. So, okay. Talmadge, I'll look for that and find it for you. Oh, will you guys give these back to me, please? Sorry, I forgot to get them. Huh? No, just this. These as a group. Thank you. Your final is on the target date. Tuesday? Is it Thursday? it's the time that it is on Slick's website. Thank you.
And then
Thursday from 9:10.
I actually do run anatomy lab stuff. I'm the director, but we don't provide those pieces.
Oh, you don't? So, most of the videos practice, like watching videos and practice, and then we would post like the key.
Well, then he might. Yeah, he might be some. Who is that, Jeff?
Yeah.
Yeah.
I just can't find it anywhere, so I can take the practice.
Just ask. Yeah, that's nice. I don't have them. How much? Let me look for your time.
Hey, I have a quick question. Can we answer Alveolar's capsules start glomerular capsule?
I'll make it work for everybody. Did you already look through all of those?
I'll check again.
Your fifth book uses Bowman. This still uses all of those.
I think it's there. No, yeah,
Yeah, you can just stick it right there.
thank you.
It's not that big of a deal.
I know, but I mean, it exists somewhere. Okay, I will look for it. I'll find it for you.
Sweet, thank you.
Okay. Yes. So that is not your bottom.
Are you gonna be at your office today?
Yep, I'll be there in just a minute.
So with the, and I will get to this next time, but for alveolar to expand, it has to, the intrapleural has to be less than LV.
Yeah, it is. Yeah.
So that graph is kind of maybe a little bit,
This is assuming that this one right here.
yeah.
This is assuming that the lungs are adhered to the wall.
Okay,
This is
okay.
assuming a negative intrapleural pressure.
Okay,
Yes.
Sweet.
Why are there people in here? Do you guys have a review or something? Oh, I was like, what the heck? Because there's never anybody in here right after this.